Okay, hello everyone. I think today everything has been set up again correctly, so we can hopefully go through this live lecture smoothly. So the topic of today's lecture is going to be parametric PDEs. I plan to cover quite a bit of material, so I'm going to get right to it. So parametric PDEs are really kind of the thing that we want to solve with reduced order models, with model reduction. So all the problems that we've seen in the introduction and that we'll see in our project sessions and whatever we talk about model reduction are going to revolve around parametric PDEs. So I feel like I have some feedback on the sound. Sorry. Yeah, okay. Okay, so what exactly is a parametric PDE and why are we interested in these? So I would say that a parametric PDE, we're interested in these when the physical system that we're interested in depends on parameters, right? It's kind of in the name. So when the physical system that we are interested in depends on parameters. Okay, well, does this happen a lot? Yes, it does. We can kind of distinguish between a couple of examples here. For example, we have when we have different material parameters. This could be if we're trying to optimize a structure and we're able to give different components different stiffnesses, or if we're trying to optimize sort of a heat sink where each metal has different heat properties. In the introduction I gave some examples of multi-scale situations where in that case we're talking about plant material and each point in the plant material was based on an underlying scale level. And that again depends on a couple of parameters, right? And we had to do many of those computations for many different types of material parameters. Well, that's exactly where we use a reduced order model for. So this happens quite a lot. What's another example where we see some parameter dependence? Well, for instance, if we're interested in a real-time response to some parameter-dependent input. So real-time response to some input. So that might be the case if we're modeling a robotic arm that gets forces as input, or an entire aircraft, right, where the input is also sort of aerodynamic forces, and we're trying to predict how the system is going to respond based on our actions and based on the different parametric inputs. Now, another parameter dependence that's maybe slightly less obvious is if we might have like a geometric variability. So where would that occur? For instance, again, design optimization is a clear example. If we want to design a certain structure and we're able to vary some geometry of components at certain thicknesses. One example that we're running right now actually involves a multi-scale behavior as well for a human liver, so biomechanics, where each compartment also can be distorted. So we're interested in solving really fast many of these multi-scale problems where each compartment is distorted geometrically. And then again, we're talking about a physical system, and we have some parameters that are going to change that physical system, and we want to solve really fast each of the for many different parameters what our solution might look like. And that is what reduced order modeling is really about. So can we draw some examples here? So what we might look at, I think because we're talking about solid mechanics mostly, I'll focus on that. And most natural for that would be some sort of design optimization again. So suppose that we're designing sort of a bridge, and each of these members has a certain area. So right now our physical system, the bridge, depends on its response. It depends on 7 parameters. Right? Those are the 7 area. So this is in a sense a 7-dimensional parametric problem. And for each of those different choices in parameters, we might have some design constraints, a maximal deflection, and at the same time we might want to minimize the material used. So in our design optimization, we would shuffle around these areas to see our best design spot, and at each choice of parameter point, each choice of set of A1 through A7, we would need to solve the whole physical system again. Well, okay, this is a discrete solution, it's relatively small, right? We might only have the degrees of freedom that are represented by the nodes, so it might only be like a 10 or 12 dimensional problem, so that's not really the kind of complexity that we're focusing on here. But suppose that we might have something like this, where all we're really trying to do is optimize a block of material, and suppose that we are able for some reason to specify the material stiffness E as well as the Poisson ratio mu for each of these different blocks. Yeah, and I could for instance think about, I don't know, if this is a 3D printed structure, or if these are somehow different soil components in the grid. And well, I'm just coming up with some examples here, but suppose that we want to have multiple load cases, a shear load and maybe also a tensile load, and we might want this special material to be stiff in one direction and flexible in another, right? So now, how many parameters do we have? Well, we have 9 of those grids. Each of those have 2 parameters, so we have 18 parameters. And for each of these parameters, we would have to solve this system. And right now, this is no longer as simple and discrete as the first example. So we might actually create a large finite element system to solve something like this. And of course, this is still a rudimentary example, but it might be more sizable. And we might have to solve then that very expensive finite element simulation for a whole bunch of parameter points in order to come up with either a best design or something like that. Yeah? So that is in quite a general sense what we're trying to do here, and what parameterized PDEs are about. There are a bunch of parameters that influence the physical system. And our objective is to answer the question, given a set of parameters, which will be E1 and nu1, E2, nu2, etc. What is the solution of the PDE, or the physical system? So we have here now a set of parameters, and the way that we're going to talk about that as a point, the set of parameters is a point in a parameter space. And the symbols that I'm going to use for that is that any point in our parameter space is going to be denoted by mu. So mu is a parameter point, which is really just a tuple of a couple of values. So for the right example, that would be E1, nu1, E2, nu2, etc. And these are going to lie in our parameter space, which I'll denote with this P. So a parameter space at this point is all the possible parameters that we permit, that we allow. Yeah? So this is going to be, since each of these is stiffness and a Poisson ratio is going to be a scalar, this will be some subset of our, and I said I had 18 parameters, so this is going to be R18. Yeah, it's going to be a subset of that. Of course, we're not interested in all possible real values for the stiffness and the Poisson ratio, so we're interested in a subset of that R18. Okay, so here we say that mu is a parameter point. In the parameter domain P. And that parameter domain P is, in our case, well, okay, 18 dimensional. So what might our parameter domain look like, our parameter space? Well, for the example that we have Young's moduli and Poisson ratios, this might, for instance, be, let's see, so we might allow our stiffness to vary, for instance, from 50 megapascals to 100 megapascals or 200 megapascals. And we might vary our Poisson ratio from, what did I write down? So like 0.25 to 0.35. So I think I took some random values here from 3D printable materials to keep with that example. And this is going to be raised to the power of the amount of squares that we have is 9, right? So that's an example of a parameter space. And again, there's a whole bunch of points in the parameter space, and in principle there's infinitely many. And for each of these infinitely many points, we might want to explore what the solution looks like. And then we want to choose the solution that best fits our design parameters. Okay. So a parameterized PDE, what that now means is that at each parameter point we have a new partial differential equation. So at each parameter point we have a new PDE, parameterized partial differential equations. So if I write my partial differential equation in the strong form with these operators, right, this was now a differential operator, then this differential operator L, well, it's going to depend on my parameter point. Right? So I have a subscript mu there. And this is going to act on some solution field. And again, in this notation, we're interpreting L as a mapping from subleft space to another subleft space. And we're looking for the mapping such that this is equal to our right-hand side forcing. And even our forcing might depend on the parameter point, right? That's one of the things that we said as our possible options. That's the response to input. And so both our PDE as well as our data, our right-hand side, might depend on the parameter. Now we also said that strong forms and weak forms are equivalent. So the equivalent way of writing this is that we have some bilinear form with a test function and a solution function, and this bilinear form now depends on a parameter mu, such that that is equal to some linear form v, and also that linear form might depend on mu. Okay, so now I'm working quite abstractly, like let's try to do this a bit more explicitly, and again we'll take the example of that block of different materials. So clearly the partial differential equation that we're dealing with there is elasticity, and we'll stick to linear elasticity. So the PDE would be that minus the divergence of our stress, which is a stiffness tensor. And this stiffness tensor, this one now depends on whatever material we choose in each of these arrays. So this is where our parameter dependence hides in. And so I have a stiffness tensor that depends on our parameter point in our parameter domain. And then we have the second double contraction with the symmetric gradient of u, and that is going to be equal to, well, a forcing. And in our example, the one that I just posed, our force actually does not depend on the parameter, so I'll stick with that for now. Now, what is the equivalent bilinear form? Well, we talked about this a couple of times. This would be that the integral of the symmetric gradient of our test function double contracted with our stiffness, which again is dependent on our choice of parameters, double contracted with the symmetric gradient of a solution, would be equal to the integral of some force with v. Okay, so this is in a rather general sense what a parametric partial differential equation would look like. But we're going to pretty much for the rest of this class talk about a very specific form of such parametric partial differential equation. We're going to be focusing on parametric partial differential equations that can be affinely separated with respect to their parameters. And so we're going to consider problems with affine parameter dependence. Now, what does that mean? That means that both our bilinear form and our linear form can be written in the following way. That we have the bilinear form of our test function, our solution function, and at any parameter point mu, that can be written as a sum of a certain number of, well, more separated bilinear forms, and I'll sum over a number q. And these new bilinear forms, they are independent of parameters, so they're simply u and v, or let me stick with v and u. It's just a notational difference, but I'll be consistent. And each of these bilinear forms, well, they depend on the parameters only in a sense as a multiplication. And a multiplication might not be multiplication directly with the parameter, but some multiplication with some function that depends on the parameter. And those functions are called, or I'll write those as theta. And again, we have now q of these thetas, and well, the amount of terms that we have here, that might change per situation. So in general, we have a number q, and I'll write qb to indicate this is for the bilinear form, and I also have to add a superscript b for the theta, because we're going to assume the same thing also for the linear form. Yeah, but I want to rehearse this a little bit. So we're going to assume that our bilinear form, which encodes the partial differential equation, that can be written as some summation of bilinear forms independent of any kind of parameter multiplied by some function of parameters. And we assume the same thing for our linear form. Again, this can be written as the sum of q and now ql, because these might not necessarily be the same number. In fact, if L is independent of the parameter, that would cancel altogether. Of other thetas, again, these might be other functions. And those thetas, they depend on mu's, our parameter points. Oh, that's of course not a b at that point. With separable linear forms, and each of those linear forms is independent of a parameter. So this is saying that our problem has affine parameter dependence. And this is actually going to be extremely important for a number of cases, or a number of reasons. Firstly, this is going to help in the analysis of the problem. So this is going to be important for problem analysis. So what I mean by that, well, this is actually the thing that we'll focus on most during this lecture. This means that we're going to talk about how stable is my solution based on the parameter, how much does it fluctuate based on the parameter, how well can any possible solution be represented by a reduced basis method. That analysis all hinges on the assumption that we can separate our bilinear forms and linear forms as written down right there. Now, another reason to do this is that we see right now that if we want to address a new parameter point, well, then we only have to compute those thetas again. So that the b's remain and the l's remain the same. So for every new parameter point, we only have to assemble, well, we don't have to assemble those b's and those l's again, or if I say that slightly differently, only have to assemble the b and the l's once. The BQs and LQs once. So we do that once beforehand, and afterwards we can create a new system of equations that corresponds to a new parameter point in our parameterized PDE, simply by summing again all these different stiffness matrices and force vectors multiplied by different weights now. Now mind you that that would still be an extremely expensive thing to solve. If we want to do this accurately, we might need hundreds of thousands or millions of degrees of freedom. So this is still talking about the high fidelity system of equations. Also looking ahead, once we form some form of reduced basis method or reduced order model for this, then we also rely on this affine parameter dependence and being able to assemble that quickly. Yeah? And this is actually a very major point in the story. So we're able to do fast assembly of the reduced order system during operations. Reduced order system during operations. You've already seen this a little bit in the second project, where I'm asking you to reduce the large mass in the large stiffness matrix into very small mass and a very small stiffness matrix, which would only be a 4x4 matrix. Well, we can only do that for every possible parameter point if we have an affine parameter dependence that looks like that. Now, is this always the case? Do we always have some sort of affine parameter dependence hidden in our PDEs? Well, the answer really is no, we don't. For nonlinear problems, we don't. If our material parameters depend on the complete spatial domain and vary from point to point, we would not have an affine parameter dependence. But these points are so important that even for cases like that, we will actually force it to be of this form, and we'll do so by some sort of modal decomposition of actually our stiffness matrices and our force vectors, and we're going to rewrite those as some sort of some sum that does satisfy this. And that will be an approximation as well at that point. But just to illustrate how important that these properties are, but even if it really doesn't fit, we're going to make it fit. Okay, so let's take a look at the example that we wrote down for the linear elasticity case. Does this satisfy these points? Well, in the sense that I wrote it right now, it actually doesn't quite look like it, because I have my parameters stuck way in the middle of my weak formulation. There's no way that I'll be able to pull something out up front. I cannot rewrite this into a stiffness tensor that somehow sits in front of the bilinear formula, so we somehow want to have something there. Yeah? So how would we do that? Well, actually we can rewrite the stiffness equations a little bit, and they would satisfy this form, so let me do that as an example. And the first thing we need to do is, we realize that we have a couple of separate domains. Each of these blocks is a separate domain, so we can rewrite this integral over the complete volume as a sum of integrals over the different volumes, which already removes part of the spatial dependence of the parameters. And it already starts to look a little bit like that affine decomposition. So for the linear elasticity example, firstly we're going to write B V U mu and simply as the sum of each of the 9 blocks, where we have 9 subdomains, and we would still have the same expression. And actually our force vector, well, it's simply, it's not dependent on the parameters, so we naturally have a decomposition like that. It's only a single term. Now again, this is not yet exactly in the form that we would like to have this, and we have to rewrite things a little bit. And as you may know, the linear elasticity equations, they decouple in a whole bunch of ways. We can use the Young's modulus and the Poisson ratio, or we could write using a bulk modulus and some other parameters. And the way that actually fits this setup is using the Lamé parameters. And the way that works is that we write our stress, so our stiffness tensor double contracted with our strain, which again is our stress tensor. Then we will write this as 2 times the shear modulus, which is a function, and this is where our thetas come in, which is a function of a Young's modulus and a Poisson ratio, times the symmetric gradient of U, plus, I think that's Lamè's second parameter, lambda, which is again also a function of E and mu, times the trace of our symmetric gradient times the identity tensor, second order. So this is just one way to write the constitutive law. And the nice thing about this is that we can already see, well, we have certain multiplications with independent parameters, which we in the end will be able to separate out of our integrals. So, continuing with the bilinear form, we would now be able to say that is equal to, again, the sum over our 9 subdomains. 9. Of, well, this guy, at each subdomain, that is a constant, so I can pull that out of the integral. So I have 2g, and again, this is a function of E and nu at q, multiplied by the integral over that subdomain times the symmetric gradient of v, double contracted with the symmetric gradient of u. And we have another term, so let's close this, d omega plus lambda times e q mu q times the integral over that subdomain omega q times, and I'll write this down first and then I'll talk about it. This is the trace of the symmetric gradient of the test function times the trace of the symmetric gradient of our solution. Okay? And the way that this works is a slight index trick. That is because if I double contract the symmetric gradient or some second order tensor with the identity, so if I have, let me say, a second order tensor A double contracted with I, and that will be simply the sum of the diagonal entries, which is simply the trace of A. Yeah? So that's coming from there. Anyway, that's not really important for my story though. What is important is that we see now that even though it didn't quite look like this beforehand, we now have this affine parameter dependence that I was talking about, where this would be some theta of a parameter point, right? And again, a parameter point is some point in a high dimensional or higher dimensional parameter space, which includes all the parameter, the e's and all the nu's. Yeah? So this would be some, I would almost call this theta bq1, and this would be theta bq2, also depends on the parameter point in our parameter domain. Yeah? And this would then be also a bilinear form, q, and let's call it 1, of v and u. And this is also a bilinear form, q2, of v and u. And as you can see, those bilinear forms themselves, they do not depend on the parameters. The parameter dependence is purely in those the factors up front. So indeed this satisfies now this assumed affine decomposability. Yeah? So this is of the form that we talked about here. Okay. So that is going to be a very important thing that I'll rehearse a couple of times throughout these lectures. We'll see this all over the place, and this is really going to be a core assumption. And we'll also see that already to be of relevance today. So how do we continue from here? Actually, a large part of today I'm not even going to talk about reduced order models. I'm going to talk about the parameterized partial differential equation and what we can say about these. And the first thing we're going to do is we're actually going to solve our parameter dependent partial differential equation using a finite element mesh. And we'll use a finite element mesh that is so fine that we pretty much have no difference between the exact solution and our finite dimensional finite element solution, which is still might have hundreds of thousands or millions of degrees of freedom. So the first thing that we're going to do is we're going to replace the original formulation that was right here, which really involved functions in Sobolev spaces in H1, we're going to replace that with a high fidelity finite element problem. So now we replace this by a high fidelity finite element problem. And that problem statement would look like: find some discrete solution or finite element solution UH in a finite element function space, also UH, capital U, which will be, as we typically do with finite elements, the span of a whole bunch of basis functions, n, x, I, where we have a span from I is equal to 1 to some number n. And at this point we're going to assume that this number n is actually very, very large. Yeah, so we're going to look for a solution that lies in this space. It's going to be very expensive to find, but still such that, well, the bilinear form of UH, V, again a parameter dependence in there, is equal to the linear form of V, which also might have parameter dependence. And that has to hold true for all possible test functions V, also in UH. Yeah, so again, at this point we assume that n is very large. And by that I mean that my finite element solution, that is going to approximate the real solution to a very high degree, and we're referring to our discrete approximation now as the truth problem. Okay. Okay, I'll refer to this equation in a second, so I'll give this a number or a symbol. So what we can do right now is, even though this might be very, very expensive, and the objective is to make exactly this a cheap procedure, what we can do is we can pick a certain parameter, we can assemble or create our finite element formulation, which is actually a relatively cheap procedure because of that affine decomposability, and then we could solve that system of equations. And that part is still extremely expensive, and that's what we do, so the models still want to make cheap. But hypothetically, we'd be able to do this, given enough computation power for every choice of parameter point, and we might be able to pick, or we hypothetically could pick every single point in our parameter space and come up with a solution. Yeah, so hypothetically we could create a map that maps our parameters to our discrete finite element truth problem. Yeah, so for each, or for every parameter point mu, which lies in our parameter space, the finite element formulation gives a solution UH, and again this now naturally depends on the solution, or on the parameter point. Now that means, so there exists some map, which I'll call phi, that takes a parameter point and gives us the solution. I'm abusing notation a little bit, but I'll stick with this. Okay, so we're back to the nomenclature of mappings. That was the second lecture. We can actually draw some conclusions about stuff like that. So I'm going to rehearse the main terminology that we had, recall, because what we talked about these mappings, we said that a couple of things were important, a couple of domains, namely, or a couple of subspaces, namely its domain, its codomain, and its image. Now what were those? The domain is the possible range of inputs. So those are all possible inputs that I will allow myself to feed to this mapping. Well, that is precisely our parameter space P. Now there might be only a couple of points in there, so this could be a discrete space, but this could also be a continuous space. You might have some subsets of the real number line, so this could be there could be infinitely many points in there. Then the codomain was the global space to which our mapping maps, and that is precisely UH, the capital U. Yeah, so that is all possible finite element solutions. So this is our codomain. And now what I can do is I can take every point in my parameter domain and map it to the codomain using our mapping phi. And what we would observe is that, well, these actually don't span the complete codomain. They only span a subset of the codomain. And that subset is what we call the image. And this is already illustrating the main point that reduced basis methods and reduced order models in general kind of revolve around, and that's the fact that, well, we're not interested in all possible solutions in our very high dimensional finite element space, which again might have millions of degrees of freedom. We're really only interested in a subset of those. Yeah? And if that subset is somehow narrow enough, then maybe we could use smart functions that properly span all possible solution states. Yeah? So that's a general idea of reduced basis methods. Now I'm getting a little bit ahead of myself though. First I want to get some additional terms in there. So first of all, the image, the shorthand or written shortly IM, of the mapping phi, well, that is exactly phi of all possible points in our parameter domain, so phi of P. So those are all possible solutions. That is pretty much the set of all possible solutions. And as there might be infinitely many parameter points in our parameter domain, there would also be infinitely many solutions. So the name that we have for this set is called the solution manifold. So this set, the set of all possible solutions, is called the solution manifold. We denote this with an N. So again, if I want to use my set notation, then I would say this is the set, curly brace, of functions U in UH in the finite element, the high fidelity finite element space, that satisfy the condition that there exists, that is this backwards E, that means there exists some parameter point mu in P such that phi of mu is equal to UH. Yeah, so that is just a way of writing that set. All possible solutions. So the general objective of reduced basis methods, and let me start with the standard finite element method really. So a standard finite element method is to use a whole bunch of these, well, pretty not so smartly chosen basis functions. And of course we have reasons for choosing these, but still within the story that I'm going with, this might not look very smart. So we might have n1, n2, and each of those is dependent on position, of course, all the way to n, where n is very large. And the objective of a reduced basis method is to say, well, actually, maybe that's not the best way to do this, because a whole bunch of these degrees of freedom, they might not be relevant, or they might always be connected to one another. So what we're going to do instead is we're going to use a very low dimensional space of smart basis functions. Yeah? So a smart basis function might, for instance, be a sine. Another one. Yeah? So we might instead choose n tilde 1 and n tilde 2. And again, these are spatially dependent. So rather than looking for a finite element solution that lies in this UH, which is the span of those hat functions, you might look for a solution in that space that is spanned by these smart basis functions. And what we really want to do is to choose those smart basis functions in such a way that the span that I wrote here, that approximates that solution manifold as best as possible. Yeah, so this span is very close to the set of all possible solutions. So all possible solutions are almost spanned by just a very small number of smart basis functions. Yeah, and the difference between various reduced basis methods is exactly the approach that you might use to come up with these smart basis functions. Yeah? And well, the first one we've already seen, that was model decomposition. So model decomposition would be an example of a reduced basis method. So we used an eigenvalue problem to come up with these smart basis functions, and with some analysis we actually know that that is a pretty good span of all possible solution states. And even though we weren't really talking about the parameterized PDE back then, or what you're working on right now probably, you could look at the solution manifold as all the possible solutions in time. And then we found that actually the first few eigenvalues or eigensolutions actually span all those solutions in time pretty well. And each solution in time can be written as a linear combination of a number of these eigensolutions. Span again is any linear combination between those components. Okay, so many of the things I'll talk about are different approaches of obtaining precisely those smart basis functions. But that is actually something that I'm gonna not do today. First I'm gonna address some more underlying questions. And really the underlying question that is of prime importance before we start trying this is to find an answer to, can we effectively do this? And I've decomposed this question into two sub-questions which I think answer this pretty well. First of all, this concerns the width, in quotation marks, the width of the solution manifold. Yeah, and just to make sure that this is clear, so the question, can we effectively do that, is based on this statement. That we have some span of just a number of basis functions such that pretty much overlaps, so it's very close to the solution manifold, the set of all possible solutions. And that relies on those 2 points. Firstly, is this concerns the width of the solution manifold, which is really a question that concerns, is this hypothetically possible? And the second question is, or the second requirement that we really have is regarding the smoothness of the solution manifold. Then I'm putting this in quotation marks because I'll address exactly what I mean by this in a second. So the width and the smoothness of a manifold. Firstly though, the second point, what is that about? That's really about if this is practically effective. So the first question, or the first property, the width, is about if this is hypothetically possible, and if this is smooth or not relates to if this is practically effective. So let's try to visualize this a little bit, and I'll draw a couple of graphs. I think I'll draw 4. And I'll draw different solution manifolds in each of these graphs to get an idea of what that might look like, what that really is. And then I'll address these questions. Is this wide? Is this not wide? And is this smooth or not? So I'm drawing this in 2D space, which is already quite a limitation. Of course, in reality, our solution manifold would be some subspace in 100,000 dimensional space, right? All the degrees of freedom in a finite element mesh. But right now, I'm sort of assuming a situation where I only have 2 degrees of freedom. So I have degree of freedom 1 and degree of freedom 2. So I have some parametric problem that has only 2 degrees of freedom, I suppose. And suppose that I pick a parameter point in my parameter domain and I get a solution that lies right here. And then I move my parameter point a little bit and I find that the new solution lies there. The next one lies over here and over here. And by going through all of these steps, I might end up with a set of all possible solutions that would look like that. Yeah? Etc. So this is the set of all possible solutions given if I range over my parameter domain. So this will be n. Now, is this a wide or a narrow solution manifold? Well, I would say, even from a geometric perspective, the width of this graph is pretty extensive. So this is not a very thin, or I would say, yeah, this is a very wide solution manifold. And that is not a good thing. What we want is a solution manifold that is narrow, because right now all our solutions, they lie so far apart and they scatter our domain so far that there's really no way that we can probably or possibly reduce this, this solution space. There is no one-dimensional space that properly spans this solution manifold. Yeah, so that is not the type of problem that we can even begin to address with the reduced order model. Yeah? So what might be? Well, okay, so then maybe the next intuitive way of thinking about it, would it be something like this then? Well, the answer is, well, okay, so this is much thinner, it's not as wide from a geometric perspective even to the example on the left, but there's also no way that we can find a one-dimensional system that properly spans this. So even though this is not very wide, we're still not so happy with this. This is not something that we can dimensionally reduce. So then what is something that we would be happy with? Well, consider this solution manifold. So again, this is the solution manifold. Consider this solution manifold. Might look something like that. This is something that we're happy with. This is a very thin manifold. So this is something that we're happy with. So this already begins to give a physical or an intuitive interpretation of what I mean by wide and thin. I don't mean the literal span of all possible solutions. I mean, given that I only have 1 degree of freedom to spare, how well would I be able to approximate all solution points in this manifold? Yeah, so this would be its width in the sense that we're talking about right now. So it's fine if our solutions lie in a very broad spectrum, as long as that spectrum can be well represented by a finite or a smaller dimensional subspace. And that's exactly what the width of a manifold is about. And we'll actually come back to that in just a second and make that a little bit more specific. So I haven't talked about smoothness yet, but I will be able to say already, well, actually this line looks pretty smooth. So we're also quite happy with that. So this is actually the perfect example of something that we would be very effective with in producing a reduced order model for. Now, what would be an example of something that is thin but not smooth? Well, that might be something that looks like this. I'll actually try and make 2 points with this graph. So again, this might be pretty thin. I'll actually say very thin. So that is something that we're happy with. And how can I see it? Well, again, if I have only one degree of freedom to spare, then I could create a subspace that spans that line. One-dimensional subspace is a line. And every point in my solution manifold lies pretty close to that line. So it's pretty thin. But clearly it's not very smooth, right? This is going up and down. And I want to give another example of something that might not be smooth, even though it looks smooth, and that's actually the line on the top right. Suppose that I have a bunch of degrees, or each of my parameter points kind of a line like that. At some point they start drifting away, and they start making very, very large jumps in the solution manifold for only small changes in the parameter. So that would also be an example of something that is not smooth, even though it lies on the line. Yeah? So the smoothness in this sense is about, if I change my parameter a little bit, how much does my solution change? So this is not smooth. And that is something that we're not happy with. And again, it is not smooth here. That was clear. But it might also be not smooth here. Again, based on how these parameters are spaced in the solution manifold. Now, why is that actually important? Well, if we find out, or if we end up getting a reduced basis method, so only a couple of smart basis functions, and we produce a finite element system of equations for that, and we try to solve for a new parameter point. So I'll take parameter points here. And we would try and obtain a solution there. Well, the whole partial differential equation, everything is so sensitive to the parameters that even though I might be able to hypothetically approximate that point pretty well, due to all kinds of instabilities, I might end up with a solution that completely overshoots that. Yeah? So again, the thickness or the width of the solution manifold, that is it hypothetically possible to reduce my manifold into a smaller dimensional subset that can be spanned by a couple of smart basis functions. And the smoothness is about, once I've done that, will I actually be effective in creating or computing new solutions, given my reduced basis method. Okay, and now, in the last 40 minutes, I'll actually go over both these points and give some sort of more specific equations for that. So how can we determine, compute, see whether a manifold is thick or thin, and smooth or not smooth. So let's start with the first one. And the name that we actually have for the width of a manifold in this context is the Kolmogorov n width. And I'm putting down a small n here on purpose. Again, the big N would be the number of basis functions that we use for a high fidelity system. Yeah, so in all these graphs, the big N would actually be, well, 2. In a more practically relevant case, it would be millions, right? And the small n is about, given only a small number of degrees of freedom, 1 in these graphs, what is then the best way that we can approximate this manifold? That's where the small n comes. The small n is the number of reduced bases that you would use. Yeah, so for the project where you're using 4 modal eigen solutions, then the small n here is 4, and the big N depends on how many you're using. For the eigenvalue problem, it might be, I don't know, a couple of hundreds or something like that. Okay, so again, this is about how well hypothetically can M, the solution manifold, be represented by some n-dimensional subspace. Okay, so let's try and get an equation for this. And I'll draw these graphs or similar graphs one more time. So then we have a 2-degree of freedom system. I start with some parameter point, which might be at the boundary of my parameter space, and I'll trace my parameter path. Maybe I'll end up somewhere over there. Yeah, so that is my solution manifold M. So let's just take some n-dimensional subspace. So let's see, how do I write this? I don't want to write this as steps. But, okay. So let's take some n-dimensional subspace. So this is again n, big N is equal to 2. This is a 2-dimensional problem. And I'll take some 1-dimensional subspace. So let's take this line. Sorry, that was not a very clean line. And that might be a 1-dimensional. A line is a 1-dimensional subspace of the plane. So, first of all, let's try and answer some questions about distances in this graph. So, first question. What is the distance between some solution u? So I'm going to take some solution u in my solution plane, or in my solution manifold, sorry. What is then the distance between that solution, some arbitrary solution in the solution manifold, to my n-dimensional subspace? What is the distance between some solution u, and again UH, high fidelity solution, truth solution, which lies in my solution manifold, is a possible solution to my problem for some parameter. And what is the distance between that guy and our Vn dimensional subspace? Yeah? So this subspace is called Vn. And right now, of course, I'm talking geometrically, so these are vectors, but in a more general sense, Vn will be the span of a couple of smart basis functions, Intel smart basis function number small n. Yeah, so that is that. Okay. Yeah, so in reality, what we're really interested in is when these are functions. Right now, again, I'm back to drawing arrows. And I'm fine with that because, well, this was this generalized overview where magnitudes of arrows and magnitudes of functions, it all overlaps. It's all the same theory. Okay, so what is the distance between some solution, which is a function in our solution manifold, and our subspace? We'll call that d, UH, and Vn. Well, I can draw that graphically, it's really quite clear. From that point to, well, I have to go perpendicular onto my subspace. And that is what we call d, UH, and Vn. I'm actually not so happy with the point that I've chosen. I'll move back a little bit. I'll choose another point. I'll choose this point as my example point right now. So that would be UH, and well, clearly that line represents the distance from UH to Vn. And again, this line is Vn. So how do I actually compute that? Well, this distance is going to be the minimal length of UH minus U tilde for any utility in my subspace. Yeah, so I could go over every possible solution in my subspace. I could determine the length with respect to that point, and the minimal length is going to be equal to that distance. And again, I'm able to do this irrespective of whether I'm drawing arrows in a graph or functions in function spaces, because this is a generalized notation. Yeah? We also have norms for functions. We're able to measure distances of functions, even though that has a, I don't know, conceptually is maybe a little tricky. So if we're talking about functions, then this would be the H1 norm, if we're talking about an H1 subgroup space, which most of the time we are. So that is the distance between some UH and Vn. So the next question I want to ask is, what is now the deviation? What is the deviation? Between M and V. How far are these is the subspace away from the manifold in a global sense? Well, that is pretty straightforwardly defined as the largest possible distance. And again, this is why I was unhappy with my choice of point earlier, because that might actually be exactly that point. Yeah? So this distance, that is what we might call the deviation for this choice of subspace. So that's what I'm going to call d of M and Vn. That's the distance of the complete manifold with respect to my subspace. So how do I write that? I would say d of the manifold and the subspace, that is going to be the maximal distance of any possible u in the manifold, the solution, and the distance was the minimal of u tilde in Vn of the norm of those 2 points. Okay, so now for a given manifold and a given lower dimensional subspace, I'm able to say how far it is away. That's not what I wanted to do. What I wanted to do was to give a number for the width of a manifold, and that's going to be the last question. So what is the n width of M? And that will actually be the distance or the deviation between M and V when V is taken to be the optimal space. Let's make sure this is not VH, it's Vn. So again, if I try and draw that same graph, I'll get it back here. So I'll do my best to sort of draw the same thing. So I started somewhere over here, ended somewhere over here. Something like that. So the n width of M, and again, this green line is N, would be, given the best possible lower dimensional subspace, and that might look something like that. Given this best subspace, what is then that distance? So in this graph, that would either be this distance or this distance, which, if this was a proper drawing, would be the same. And that is what we define the n width of M. So how do we write that? We're going to write d n of M. That is going to be, well, the deviation, so max of UH in N, min U tilde of Vn of UH minus U tilde. So that's the equation that we had earlier. And now it's going to be the deviation corresponding to the best possible subspace. So this is going to be the minimal deviation for all possible subspaces Vn as a subspace of UH, where the dimension of Vn is n. Yeah? So for an n-dimensional subspace of my complete solution space, what is the minimal possible deviation that I would have. And clearly, if this number is very small, then I am able to approximate that solution manifold with a low-dimensional subspace. If this number is very, very large, then I'm simply not able to do that, and the idea of using a reduced automotive for something like that is not appropriate. Okay. Now, this is an equation, but of course I can't really compute anything here yet. So you can look into books and see for different parameterized partial differential equations that they come up with actual expressions for this distance. That depends on the nature of the problem. It's also a couple of pages of derivation, and I found that the results are not clear. So I'm not going to go through that. I'll give you some main conclusions about whether this is going to be small or large. But one of my main objectives here was to get you thinking about that this is actually a requirement. We can't just take some arbitrary problem and throw a reduced order model against it. Yeah, we have to think about, is this even possible? That's exactly what this is trying to address. Okay, so a couple of points then about this before I continue. So first of all, different reduced basis methods, they are actually about finding that optimal subspace. Yeah, that is also not clear. I don't immediately, I can see it from this drawing because I'm talking about a two-dimensional problem. But if I have a million degrees of freedom and a whole bunch of parameters, then it's not immediately clear what that optimal subspace is. So different reduced basis methods actually focus on the strategies of obtaining that optimal Vn. And that's the first thing I want to point out. So different reduced basis, RB methods. So reduced things, that's the first time I used that abbreviation. Reduced basis. Revolve around the strategy for obtaining that optimal subspace Vn. And again, that would be now the span of a couple of smart basis functions. One. And how many of them? Well, exactly n, right? Small n. Because it's small n dimensional. And again, the project has exactly been one of those methods. We use an eigenvalue problem to find or a small set of basis functions that span the solution space in time pretty well. And what we'll see next is proper orthogonal decomposition as a method for that. We have greedy basis construction as a method for that. Proper generalized decomposition. So those are really a forest of different methods. And their objective is always to exactly find that low dimensional subspace that spans the manifold quite well. So what conclusions can I draw about that dn, so that n width of m? Well, generally speaking, if my problem is in any way suitable for this strategy, then dn of m converges exponentially with n. Exponentially with n. Now that's a very, very nice property. What that means is that if I have 4 bases in my reduced basis space and I find that my error is too large, I'm making too big of an error, well then I just add one more and I have a much better approximation of n because it's converging exponentially. That also means that the last few, well hopefully it also means that the last few are not so important and that's really only the first that have a major impact. Then a little bit more tangible, what does the actual value of dn depend on? So what does this value depend on? Well, first of all, it depends on the parametric complexity. The parametric complexity. So those might be the theta functions. Those might be the number of terms in the affine decomposition. It also depends on the stability characteristics of the partial differential equations. So I would say these are actually quite natural conclusions. If I have a problem on partial differential equation that's going to be extremely sensitive to input, well then the n width, the Kolmogorov n width is going to be large. If I have a couple of parameters that have a huge influence on my solution manifold, well then also in all likelihood it's going to be large. Yeah? So to get any real conclusion on this, you'd have to go through those pages of derivations for your problem. I didn't find that so useful for you right now, so I'm skipping that, but I still wanted to make you have a feel for what's going on here. Okay, then we're at the last bit of the story that I want to tell today, and that is the second point that we addressed. So the first point was about the width of the solution manifold. Is it hypothetically possible to reduce the solution manifold into a small subset? And the second one was about the smoothness. And this is actually going to be a derivation, so we're going to throw in some math here. Because from this on we can actually obtain a sensible and useful conclusion. So the smoothness is going to be, well, in a very similar sense, it's going to depend on the stability of the partial differential equation, as well as the stability of the parameter functions. Parameter functions there. So that's quite natural, and we'll actually see explicitly how they depend on that. So the smoothness, as we drew here, is really a question about how far are these different points along the line from one another. And going one layer deeper, I would even be able to ask questions about the second derivative. So how quickly does that change? But I'll stick with first derivatives for now. I think that's already making the point sufficiently well. And again, we defined phi as a map that takes a parameter and gives a solution. So the question that I really want to ask is, how big is the difference between phi at mu plus some distance d in some parameter direction minus phi at my original point divided by d. Yeah, so this is really a definition of a derivative. So I'm taking the derivative of my mapping with respect, or the directional derivative really, of my mapping with respect to some direction in our parameter space. And just to be clear, mu is a tuple of a whole bunch of values, right? This is not one specific value here. In the example of the blocks, these were all the stiffnesses and all the Poisson ratios combined into one object, mu. Okay, so I'm going to talk about the stability of the PDE. That's something that I actually talk about a whole lot in a different class that I teach. So those of you that have taken that class will be familiar with some of the things I'll write down right here. But it's also something that I already kind of discussed in one of the previous lectures when we're talking about the smallest eigenvalues and their relation to stability. And then we also saw that also for a matrix equation, the difference between the smallest and biggest eigenvalues is precisely encoding sort of the stability of that matrix. So what did we say back then? We said, so recall, that just like a matrix, bilinear form has eigenvalues, and that the smallest eigenvalue is actually very, very important. So what is that? B, U, H, V. At some parameter location, right? Remember we had this parameter dependence in our bilinear form. So this is going to be larger than or equal to some constant c, which again, because my bilinear form is now parameter dependent, will become parameter dependent, multiplied by u, the norm of u squared. Now this is effectively sort of the smallest eigenvalue. And as I showed back then, this has to do with the stability of the system, in the sense that if I fluctuate my data a little bit, how much is my solution going to change? So that's going to be an important stability characteristics that we'll actually end up seeing in the final expression. But I need some more information. Also recall that, well, the whole point of this affine decomposition is that we would write our bilinear forms as sums. How many of them? Well, some QB of functions theta that depend on mu times bilinear forms that do not depend on mu. So can I also get the smallest eigenvalues for these bilinear forms? Well, I would say generally the answer to that is no, because the smallest eigenvalue tends to be 0, because it only encodes really a small piece of the information. In the example of the different blocks, any function that is not in the first block will have a zero value as the smallest eigenvalue for the bilinear form associated to that first block. Yeah? So the smallest eigenvalue typically tends to be 0, but we might say something else. So this is also Q. We might actually consider the largest eigenvalue. This is also going to be important. So now also, and these guys can have upper bounds of their eigenvalues. So the way that we write that is that these BQs, each of these, may be bound from above, so this is going to be smaller than or equal to some parameter, which I now call gamma, which depends on B and on Q, but not on the parameter, right? Not on mu, because this is due to the affine decomposition, this is exactly independent of that, multiplied by the norm of UH and the norm of V. So I would say this is sort of related to the largest eigenvalue. I'm probably making some conceptual hand-waving arguments here, but I want to give you some idea of what these numbers relate to in a more approachable perspective. So this is all for in relation to the bilinear form. In a similar sense, we can also make similar claims for the linear form. So L of V will also be smaller than or equal to some gamma related to L times the norm of V. And again, we also have an affine decomposition for L. So for each of those sub-L's, we could also define now an upper limit as such. Okay, so now I have 10 minutes to go through this derivation. I'll do my best. Yeah, okay, so what do we know? So we have a couple of these stability characteristics, smallest and largest eigenvalues. What else do we know about the solution at a certain parameter location? Well, first of all, at our initial point, phi of mu, we have that, well, the system of equations is satisfied at that point. So we have u, h, and I'll now indicate that these depend also on the parameters. But that is equal to the linear form. And also for all v in my space, right? This is exactly what defines my solution at that point. That is exactly how you would obtain that mapping, by solving that system of equations. So naturally this has to hold. And at phi, at the parameter point mu plus d mu in some direction, we have a similar statement. We have that b u h, but now at the location mu plus, oh, that wasn't supposed to be there. So d mu at some location in some direction has to equal, starting to make some small mistakes here, at my parameter point mu plus d mu in some direction has to be equal to L of v at mu plus d mu. And also that has to hold, this also holds for all possible v in that space. So naturally what I'm going to do is I'm going to subtract these two equations and I'm going to see what I'm going to get. So I'm going to subtract these equations and use their parameter affinity. And if I do that, I would obtain the following equation. So on the left hand I have the sum over QB components of, well, first I'm going to take this guy, so I have my thetas QB at mu plus d mu multiplied by these BQs for solution UH at mu plus d mu, comma V, and these guys were no longer dependent on the parameter, that's the whole point. Subtract from that, well, the first line, that is theta B Q, simply add mu, and B at UH at mu. Look at them. V. So that is the subtraction on the left hand side, and this is going to be equal to the sum over my linear forms affine dependency, which also has thetas, but these L thetas times a linear form, and these linear forms, oh, I'm going a little too fast. So these thetas are first evaluated at mu plus d mu. Yeah, I'll first write this out all together. LV, LQ, V, BQ, minus theta LQ at mu times LQ V. So that's simply a subtraction of the second, or the second minus the first, while making use of that parameter affinity. Now we already see that we can kind of collect this term and this term into a subtraction because these and these are equal. Now the same thing does not quite hold yet over there, so what I'm going to do is I'm going to add and subtract the following term. Add and subtract the sum over QBQ. I'll write it down first and I'll explain what this is. Theta BQ evaluated at mu, BQ UH, the solution at mu plus d mu, comma V. So I'm going to add and subtract this term. Does this term make a lot of sense? Well, not really, because I'm evaluating my theta at mu, and this is a solution at mu plus d mu. So there's no physical relevance to this term, but I'm adding and subtracting it, so really I'm just adding 0. But this will help me rewrite this first term a little bit, because if I subtract this term, then I can collect it with this guy. So I collect the b with the b, and I have this one minus this one. Whereas if I add it, I can collect the theta and the theta, and I can add this minus that one. And because of the bilinearity, this actually shifts inwards. Okay, so what does that mean? What do I end up with after I do that? I have again the sum of all those different affine components. And now I have, as I said, plus this guy, theta B Q, evaluated at mu plus that little jump, minus this term, theta B Q, evaluated at mu, multiplied by, well, in both cases that's the same, so B Q UH mu plus D mu in the direction. Now I'm going to add this guy again, because this was the subtraction, so I'm going to add this guy. What do I get? I get theta B Q mu b q at u h mu plus that guy. And I have still here this term to subtract. Well, this coalesces. This is bilinear form. The v's are going to be the same. So I can simply subtract that here. This is the linearity. And the right hand side is still going to be the same as we had here. So what is this giving me right now? Actually, I have a whole bunch of terms that pretty much say the same thing, that say something evaluated at mu plus d mu minus it evaluated at mu. That's pretty close to what a derivative is. So to make this formally a derivative, what we're going to do is we're going to divide by that d, the scalar parameter d. So we're going to divide by d. Oh, no, that was a typo. Divide by d and take the limit from d goes to 0. And then I end up getting a pretty nice expression already. Again, I have the sum over all those components. This guy becomes the derivative of the theta function in the direction. So this is the directional derivative in the direction of mu hat, multiplied by b q of u. And taking the limit of d to 0 means that this simply becomes uh. Yeah, so I'm not going to write all the arguments anymore. I'm going to make my life a little bit simpler here. So that was pretty much this first whole term. Then the second term is going to be theta q b q. Well, this is going to be the directional derivative of u d u h in the direction of the change in parameter, comma v. And what do I have on my right hand side? I'm not sure if this is going to fit, but I'll try. Well, that's exactly, again, it's the derivative of the thetas of the linear forms. So I have the sum over the linear forms of d theta L Q d mu, the directional derivative of theta and the direction of our change of mu, multiplied by, what did I have there? LQV. So far no approximation, everything fits perfectly. What is my objective though? My objective is to get an expression for this guy. And this is where I'm going to have to introduce all these stabilization properties, the stability properties, the smallest and the largest eigenvalues. This is where I'll be able to change bilinear forms into these norms. Yeah? So how do I do that? Well, first of all, what I can do is I can see that the sum of all these theta times bq's, that is actually exactly defined to be the affine sum of the whole b, where now I have d u h. Let me actually maybe first write, I'll add one line that says what I'm going to do just for narrative purposes. So I'm going to rewrite this equation, and additionally, and I haven't addressed it yet, I'll choose my test function, because again, this holds for all possible test functions. So I can get a nice result by choosing my test function to be equal to duh d hat. Now we'll see that in a second. So again, this term summed is nothing other than, this is exactly the definition of my original bilinear form with duh d mu, this term, and I'm setting the same thing in my v slot. Then I'm moving all the other stuff to the right hand side, is equal to the sum over the q's for b, d theta bq d mu times bq of uh, and v is again going to be this directional derivative. Yeah, I think I'm happy with that. So sorry, that's a minus. Ah, damn it. Okay, it doesn't really matter. Plus, so I moved this to the right hand side, and my the right hand side was already Q, L, Q, d theta Q, L, directional derivative of my parameter function times the LQs. Okay, and I said I needed my stability characteristics, I actually need those right now. So now I'm going to bound these things, and the first and the smallest eigenvalue, that said that this guy, I can write it as C at mu, so the smallest eigenvalue, multiplied by the norm of whatever's in those slots, which in this case is duh, the partial or the directional derivative of my solution, square, and that would be then smaller than or equal to this term, which is equal to that term. And I think I actually have to introduce absolute signs at this point. Yeah, okay. Now, additionally, what I had for each of these BQs was that the largest eigenvalue produced the following result, and now I have to do is introduce absolute signs to make this work. So that's why my minus cancels. So d theta bq d mu times, this is going to be smaller than, again, this is also going to be smaller than gamma q b, which is independent of the parameter, multiplied by the norm of UH and the norm of DUH, directional derivative. Okay, same thing for the second term, so this closes absolute sign. QL, Q, absolute sign, D theta, LQ, D mu. And this was going to be smaller than the maximal eigenvalue of a linear operator. Is a bit of a tricky concept, okay? LQ times the norm of DUH D mu. So this guy. We substituted V to be this. So here I have the square, and here I have the same term everywhere, so that's kind of nice. I can cancel those. So I'll also move this term to the right hand side, but I have one more annoying guy, that's this one, and that's the last thing I'll have to address. What can we say about this? Well, we actually reuse the statement that involved the smallest eigenvalue. That would be always be smaller than or equal to the bilinear form. Sorry, I'm now interested in UH. UH. Well, this by definition is equal to L of U, because that, because we've, that's the equality that we're starting with, and this is going to be smaller than or equal to, well, that largest eigenvalue of L times the norm of U, which also allows us to cancel this square with this term, and allows us to simply produce U, the norm of U will be smaller than or equal to gamma L over C at mu. So this is what I'll use over there. So again, I cancel this square with this term and this term. I substitute this term for the one remaining expression that still involves U, and I divide by C, and then I'm at my final result, which says that the derivative of my solution with respect to my parameter in some direction, that will always be smaller than or equal to the sum, going slightly too fast, 1 divided by the smallest eigenvalue at that parameter location times the sum of all the affine components of B, where, actually I'm going too fast, okay? I want to have this term first. So this one is a constant, so this moves out, gamma L over C mu. Again, the sum over QB, Q, of the absolute values of my theta derivatives multiplied, weighted by those largest eigenvalues of the b's. I'm sure that I'm not typing anything wrong. I think that's correct. Plus the sum over my linear form affine terms, also the parameter dependence that they have, multiplied by the largest eigenvalue of that guy. And that's the expression. Okay, so let's take a breath and think for 2 seconds about what this is saying, and that's going to be the end of the lecture. So this is saying that at any point in my solution manifold, so I solve my solution at some point with some parameters, then I know that in any direction, if I change my parameters, then my solution will never change more than this expression. And this expression is going to be divided by the smallest eigenvalues of my problems, which again was a stability property, multiplied by the largest eigenvalues. So again, we see if those differ by a large amount, then we're in trouble. We have large derivatives. And then we have the sums of these weighted derivatives of my parameter functions weighted by the largest eigenvalues of the individual components. Yeah? So once you use this expression, it's actually quite an elegant expression, and you can get some interpretation of what this is saying. And indeed, our initial assumption is correct. This is going to depend on the stability characteristics of our partial differential equation, our parameterized partial differential equation, and on the parameter definitions and their sensitivity with respect to our parameter space. Yeah? So this is precisely what we were expecting, and it ends up being actually quite a nice expression as well. So that's what I had in mind for today. So we didn't actually talk about any way yet to construct our finite dimensional subspaces that we produce our reduced basis method from, but we did a whole bunch of analysis of really the underlying concept, and I think that's quite important. As I kind of already indicated earlier, the idea is not that you throw reduced basis methods and reduced order models against any problem, right? You first think about, is this a problem that I can actually use a reduced order model for before you proceed? And that's the thing that we can address today. And we saw that that really depends on how wide our solution manifold is, and also how smooth that is. And for those we developed some expression. Yeah. Okay. I hope that you're all still there and awake. Thank you for your attention. I'll see you next time.